Are we live? All right, welcome everyone to today's afternoon session. My name is Josh Levine. I'm from University of Arizona. You may have been seeing me running around the conference. I'm also one of the Viz program co-chairs. And it's my pleasure to be the session chair today for our session on dealing with scale, space, and dimension. We have a collection of 6 awesome papers. It's actually a diverse set of papers for this conference. It's not something that I would identify as one flavor of Viz, and I think we're gonna get some really cool talks as a result. We're gonna start with our first talk called Multivariate Probabilistic Range Queries for Scalable Interactive 3D Visualization, and Amani is here presenting for us. Let's give Amani a round of applause.
Thank you for the introduction. Welcome everyone. I am Amani Ageli, a PhD student from KAUST, and I'm presenting multivariate probabilistic range queries for scalable interactive 3D visualization. In this work, we are addressing the issue of filtering large data sets, such as meteorological data sets, where each cell has multiple attributes, such as temperature, pressure, and humidity. In order to get the filtered result, we need to apply a user query, and the scalability to such data is challenging when applying a range query of multiple attributes. So there are multiple solutions to this problem. The brute one solution is called scanning, which looks at each cell with all its attributes individually. This method is straightforward, and the result is the ground truth, but it scales linearly to the input data size and the number of attributes. There are different hierarchical grouping methods that can be used, such as R3 in the attribute space and min-max octree in the 3D space. However, the R3 cannot access a subset of the attribute dimension, and the min-max ranges are much more conservative than histogram. There are other approaches that are based on bitmaps, where essentially a 1D projection of each attribute is handled separately, and also each projection is binned. However, the bitmap itself is depending directly on the input data size, so it will not scale very well to large data. Our approach is based on bitmaps, but instead of scaling to the input data size, we are scaling to the query size by using probabilistic hashing approach. We built on Bloom filter, and Bloom filter is a space-efficient probabilistic hashing approach where we take the cell ID and we apply a hash function to map the ID to a hash index. And then we use this hash index to set the bit in the bit vector. But because the size of the Bloom filter is very small compared to the data, we expect different elements to be mapped to the same bit. And then when we query the Bloom filter, this type of collision can create false positives. Adding a second hash function can help, but only to some extent, because it will be filled in more densely. So we will handle the false positive in a separate stage. However, if we look at the equation of the expected false positive rate of the Bloom filter, we see here the small n, and the small n in the equation means the number of elements that is inserted in the Bloom filter. And this is directly related to the query size. So this actually removes the dependence on the input data size. This is why we are using the Bloom filter. So back to our method, it's very similar to bitmap. So we start by creating a 1D projection of each attribute. And here I'm illustrating it with 2 attributes. Then we create bins for each attribute, and we compute a Bloom filter inside each bin. Then we distribute the cells based on their values, and we also hash their cell ID. Now, after receiving a user query, we can select individual dimensions accordingly, and we can apply then a logical OR operation of the Bloom filters on the same attribute dimension. After that, in order to actually answer the range query, we need to count the number of dimensions that contain our data element. And in this case, we can do it in the Bloom filter by counting the number of bits. So if we are doing that in a rendering pipeline, we will receive the set of all the visible cells, and then we can test their IDs against this aggregated Bloom filter that we counted in the previous stage. This can be done progressively until we actually get a probabilistic query result. If we looked at the probabilistic query result, the colorful points here are the true positive cells, the red cells are the false positive cells, and the true negative cells are the ones that have not been rendered. So in order to get the accurate query result, we need to remove these red points by either using a transfer function that sets the opacity of these points to 0, or by using scanning. And by using scanning, we need to read all the set of accepted cells again and eliminate these false positives. So at this point, we can think of different optimizations that we can do. The first one is to actually reduce the number of false positives that we are having, and also to exclude the true negative without testing all of them against the Bloom filter. And we managed to get both of these optimizations by introducing one single idea that we called supercells. So what are these supercells? If you look here on the right, this is any type of spatial hierarchy tree that is used commonly in rendering, such as oak tree. We assign a unique supercell ID to each of these nodes. And then we start again, as what I have mentioned before, that we go through the cells and we distribute them against the bin, and we also hash their IDs. But now we will go in the tree from the bottom up, and we will also hash the supercell IDs in the bins. After that, when we receive the user query, we will start from the root, and as we are traversing, we might hit an early exit case. And by hitting the early exit case, we know that all the children are actually part of the true negative cells without testing them. And because we have fewer supercell IDs to test, we know that we will have fewer false positives. So overall, by using the supercell ID during the same tree traversal that is used in rendering, we managed to skip a big portion of the total true negative cells, and we managed to reduce the false positives. So to demonstrate the performance, we are using here a GFS meteorology prediction data that is made of 1 billion cell and 8 attribute each. And we are testing it using 3 distinct queries with different dimensionality ranging from 1 to 3. And the first test here is using a Bloom filter size of 50% of the data size. So first here, the number of true positives shown in green depends on the query, and it's not depending on the method. But the number of false positives, as seen here in red, is actually reduced significantly after using the supercells. And then we can also see that the supercells skipped a significant portion of all the true negatives. Now, if we reduce the size of the Bloom filter, we can see that the number of false positives will increase, and this is why it's important to balance the size with the expected query size. So in this method that we have here, the expected query size, or the highest expected query size, was 14%. And for that, we think the second test is still working very well. However, it's also important to note that as more dimensions are queried, the smaller the query become, and also the false positive will go down significantly. Here we also show that the supercell is indeed effective, as the query time is always better with and without the step of eliminating the false positives. So to conclude my talk, we believe that we presented an interesting method that that works best for multidimensional range query, and it scales with the query size. However, we emphasize that if a given query exceeded the query size that we are expecting, the method will still work, but the number of false positives will increase. Also, I'd like to highlight the importance of using the supercells, as it's crucial to reduce the impact of using Bloom filters in our framework. Thank you for your attention.
Thanks, Amani, for the talk. I want to remind everyone in the audience that we'll be using Slido for asking questions. You can find the link to that on the virtual website. You can find it also in Discord if you're following along there. I currently don't see any questions in Slido, but I have a question for you. You were talking about doing AND-based sort of queries. I'm curious about other sort of logical queries like OR and NOT and so forth. Have you thought about implementing for that?
Can you say it again? Sorry.
Yes. Sorry, with the mask, it would have been hard. You seem to optimize for doing AND-based queries in the way you did this. How does the implementation change if you're doing things like OR and other type of logical queries, or is it about the same?
I think we can still use the same method. It's just that maybe the count that you are searching for at the end of the aggregated filter will change, but it should work, yes.
Awesome. Thanks.
Thank you.
All right. I'm not seeing any other questions. Our next talk is actually a pre-recorded presentation from Zayu Lee. Can we cue that one up?
Hi, I'm Zeyu Li from Tianjin University. I'm glad to be here to present our work. Scatterplot is a common visualization used to intuitively review the distribution of data. However, the overlap between nodes causes the overdraw problem. It severely damages visual tasks of scatterplots, such as density perception, cluster identification, and shape examination. Many methods have been proposed to relieve the overdraw. Depending on the space where the core operation is performed, they can be classified into three categories. Data space methods simply focuses on data operation and completely ignore the stuff on visual units, while visual space methods are just the opposite. Hybrid methods perform both data transformation and view transformation. Although the previous method can alleviate the overdraw, they cannot meet the following four criteria at the same time. The first criterion is mutual exclusion of data points. That is, the coordinates of arbitrary two data points should not be exactly the same. The second criterion is mutual exclusion of visual nodes. That is, any two visual nodes should not be overlapped. The third criterion is data visual space bijection. That is, there should be a one-to-one mapping between data points and visual nodes. This criterion is a requirement for information integrity. The fourth criterion is data visual space distribution consistency. That is, the distribution presented in visual space should accurately reflect the intrinsic data distribution. This criterion is a requirement for visual tasks. Taking these four criteria into account, we formalize the goal of the solution to overdraw problem as maximizing the consistency or similarity of data distribution between two spaces under the constraints of criterion 1, 2, and 3. 5 metrics are defined in our paper to measure the distribution consistency between two scatterplots. KNN preservation and displacement minimization depicts local features, while shape preservation and density preservation depict global features. Besides, we set up a comprehensive metric, overall similarity, which measures the average similarity of two distributions observed from multiple angles. For now, we have established a dual space coupling model for overdraw solutions. The core consideration of our model lay in the solution should consider the complex relationship within and between the data space and the visual space. Based on the dual space coupling model, we designed a method that can reproduce the high-quality data distribution in visual space under strict constraints. The idea is inspired by FM halftoning and image stippling techniques. Similar to them, we reconstruct the density distribution by placing nodes with different frequency. This idea is based on a simple assumption. That is, the filling rate of the colored pixels is proportional to the perceived density. In this way, the overdraw problem can be transformed into 3 key questions. The first question is how to generate a set of circles that intactly record the data distribution. The second question is how to lay out the circles in visual space to present the recorded distribution without overlaps. The third question is how to ensure overlap-free during necessary radius configuration. For the first question, we designed an algorithm called distribution transcriptor. It transcribes the abstract data distribution into a group of concrete circles without information loss. Firstly, we spreaded singularities, that is, a group of data points with identical coordinates, following the phyllotaxis of solar flowers. This operation achieves the mutual exclusion of data points. Then, we divided the space into isometric grids, and then generate several nodes for each grid. There are 2 kinds of nodes, data node and dummy node. Each data node corresponds to a data point. Hence, the third criterion, data visual space bijection, is achieved. The coordinates of each data node are inherited from its corresponding data point. Dummy nodes only act as placeholders in sparse grids. Their coordinates are randomly sampled from the grid. Donate the number of data points in a grid as num. We assigned each node with a density attribute, which is equal to the ratio of the num to its global maximum. The grid with less than k data points are defined as sparse grid. Num data nodes and k num dummy nodes are generated for each sparse grid. For the non-sparse grid, dummy node is unnecessary and only data nodes are generated. Each node has two kinds of radiuses. The first radius is called RPAC. It is the radius that the nodes of a grid exactly fill the grid. Therefore, RPAC describes the occupied space of a node in visual space. Obviously, the denser the grid, the smaller RPAC it has. The second radius is called RDraw. It is the radius used for rendering. By default, RDraw of all nodes is set to the global minimum of RPAC. To answer the second question, that is, to place the nodes generated in the first step so that it can present the recorded distribution without overlaps, we proposed a layout algorithm called polar packing. The algorithm consists of 3 steps. Step 1, calculate the distance and the angle of each node relative to the center. Step 2, place all nodes, including the dummy nodes, in the ascending order of distance. Step 3, filter out dummy nodes. At this point, we can paint a default result since we already get the location and the radius of the nodes corresponding to all data points. However, in some scenarios, the visual quality of the default result is poor. For example, for datasets have regions with extremely high density, namely HDR datasets, the distribution disappears with the default RDraw. The reason lay in the default RDraw that is determined by the densest grid is very small. The datasets with scattered outliers show another poor case. As you can see here, outliers are often hidden in the empty background and become illegible. To solve these visual quality problems, we proposed a radius adjustment model and developed a radius adjustment tool based on the model. In the model, the horizontal and the vertical axes represent the density and the radius of node respectively. The red curve presents the RPAC among different density, which is computed by the formula in the upper right corner. The scatter plot will be overlap-free if the RDraw of all nodes is lower than its RPAC. Hence, the curve of RPAC actually depicts the safe upper bound of RDraw. Based on the radius adjustment model, we developed an interactive tool called Function RDraw. It has 2 control points, high-density control point and the low-density control point. The former can only slide along the curve of RPAC, while the latter can move freely in the highlighted gray area. These 2 control points from a piecewise function called the curve of RDraw. It depicts the render radius of each node. For the region whose density is greater than the high-density control point, its nodes are tangent to each other. Therefore, the perceived density here is 1. For the regions whose density between the 2 control points, their relative densities are maintained. The tool allows users to quickly adjust the RDraw to improve the visual quality while ensuring no overlap occurs. We conducted a series of quantitative evaluation on our method. The comparisons with 6 state-of-the-art methods on 50 datasets and 6 metrics show that: first, our method achieves the best or near the best performance on all metrics. Second, our method takes great advantage on computational efficiency. Third, our method presents strong adaptability to HDR datasets. The time complexity of our method is n prime square n prime, where n prime denotes the number of nodes to be packed, including data nodes and dummy nodes. It only takes 10 seconds to place 1 million nodes on an ordinary PC. With the increase of parameter size, all metrics show a trend of deterioration. However, on the whole, our method is quite robust. The shapes, curves, textures, outliers, and singularities shown here demonstrate that our method can uncover details hidden by the overdraw. High-grade and D-grade, as the only 2 methods that adapt to large-scale scatterplots, suffer from the crowding issue, leading to distortions in shape and density in high-density regions. By contrast, our method gets rid of the issue and maintains a high-fidelity distribution everywhere. Besides, our method can present rich and intact details with zoom interaction. In summary, In this paper, we contribute a dual space coupling model to present the complex relationship within and between data space and visual space to solve the scatterplot overdrop problem. The proposed model introduces a new design space for promising overlap removal algorithm and the interaction paradigm. We also develop an overlap-free scatterplot method on the basis of the model, which shows competitive advantage compared with the state-of-the-art methods.
All right, let's thank the speaker. Give us a second while we switch to Zoom. All right, Ziyu, can you hear us?
Yeah, I can hear you.
Excellent, you're live. So folks, if you have any questions, a reminder to again, please use Slido to post those questions. But to get everyone started, I had a question for you. I'm curious a little bit about the interaction from the user's perspective. You did an awesome quantitative evaluation of your work, but I'm wondering a little bit about what happens when a user sits down and uses the tool. Did they find it easy to use, difficult to use? Did they enjoy using it? Do you have any kind of informal feedback on that?
Well, we did not do the user study, but the tool is very easy to use. You can just move the two control points to interact with our tools and to affect the density distribution. As shown in the video, you can just move left the high density point to overcome the problem that's faced by the high density area, and move up a little about the low density point to highlight the outliers. So it is very easy to use.
Excellent. Thank you for that. And I'm not seeing any questions, so I'm going to ask you another one selfishly. I'm curious a little bit about the problem when you have multiple classes in the scatterplot. It seems like what you do is you have one global optimization. Have you considered doing separate optimizations for each class independently?
All the classes are treated as the same. We don't have to do any specific settings for each class. So every point is just colored by the label. In our tools, there don't need to do anything special.
Thank you for that. So with that, I think since there are no more questions in Slido, we're going to switch to the next talk. Thanks so much to you for being here virtually. Okay, so for our third talk today, Sarah is going to be presenting for us measuring effects of spatial visualization and domain on visualization task performance, a comparative study. Welcome, Sarah.
Thank you. Thanks everyone for coming to our talk, Measuring Effects of Spatial Visualization and Domain on Visualization Task Performance. This was a comparative study run by myself, Sarah Tandon, Alfie Abdul Rahman, and Rita Borgo at King's College London over this last year. So what I'm going to do is start out by having you imagine that you do the job of every Londoner you meet on the street. You are a business consultant at a consultancy, and you have been contracted by your local government to advise on some COVID-19 health policy. So in this room, there are going to be a lot of lawyers and politicians, and they're going to be asking for your advice. So you decide to go back to your consultancy, and you work with your math and computer scientists, your data scientists, who are spewing out some statistics and data for you in order to let you present to these lawyers and politicians in the room. So we thought about these 3 different groups, and we were starting to wonder if the types of charts and graphs that we're making for them are really effective for all these different people, given their different cognitive abilities, their different education backgrounds, and then their different motivations around approaching data visualization in the first place. So our motivation here was to empower designers to create high-impact and cognitively appropriate visuals for their communities by tying together spatial visualization, which is our chosen cognitive ability, to their domain experiences. So we've got our 3 different groups, our business participants who have high interaction and needs for domain-focused data visualization, and then they have reportedly lower levels of spatial visualization. We've got our lawyers and political scientists who have low interaction with data viz in their domain, and then also lower levels of spatial visualization, and math and computer scientists who have higher interaction with data visualization, as well as high levels of spatial visualization. So go you. We had 4 hypotheses. Our first one was that spatial visualization would differ between our different domains. Second, that performance, which for us was accuracy and response times on the visual tasks, would correlate with spatial visualization across all of our participants. And then our third and fourth hypotheses were tied that performance will vary between disciplines according to their spatial visualization ability and then also according to their domain differences, which for us meant how do they approach data visualization? Are they confident when they approach data visualization? What are they thinking before they get to an interaction? So to test our hypotheses, we came up with a 2-part online study that we crowdsourced and hosted through Prolific. The first part was a long-held psychometric test of spatial visualization. It's called the paper folding or punch test, wherein a piece of paper is folded and then a hole punched, and participants are asked to unfold the paper in their mind and imagine what it'll look like. And then for part 2, we were really inspired by COVID-19 dashboards that we saw with a lot of rotated charts. So we wanted to use charts and graphs that were familiar to the public to increase the impact of our design implications. So we came up with 42 total questions, and we ensured the questions were systematically, they covered a range of cognitive load by altering over 2 densities, 4 chart types, 3 levels of task difficulty. Questions included value search for multiple targets, as well as computing a derived variable. And we also aim to have balanced samples between gender and then participants from both the Global North and the Global South as well. We ended the part 2 with a data visualizations motivation assessment, so that's how we targeted our different domain differences. This is some example of our stimuli. We formed them keeping in mind that spatial viz directly affects the ability to compare visual encodings and layouts quickly and accurately. We chose these 4 as they're topologically equivalent over the Cartesian coordinates. On the left here, we've got the vertical and horizontal bar chart, and then rotated along polar coordinates on the right, the radial bar chart and the circular bar plot. We chose to display in every question 2 spatially rotated charts side by side to assess performance, which simulates the same cognitive processes that are involved in spatial visualization assessments. And then we ensured that each chart was displayed on the left and the right. We kept grayscale charts, and then we opted for tasks that were common to the COVID-19 data that we were using. So what were our results? We analyzed performance across density, chart type, task difficulty, over our different balanced samples of our domains, over 90 participants. So we found that lawyers and business participants had similarly low levels of spatial visualization compared to math and computer scientists who had higher levels. Again, congratulations. And then we confirmed our second hypothesis that spatial visualization level does affect response times and a moderate amount of accuracy. So in the chart on the left along the x-axis, spatial visualization is increasing, and then you can see accuracy moderately increasing. And then the chart on the right, as spatial visualization is increasing, response time is decreasing. So how did our different domains do? For response time, we found that lawyers and math and computer scientists were similarly very quick, while business participants took quite a longer time across all the densities and chart types and task difficulty. And then for accuracy, our lawyers were less accurate than our business and math and computer science participants. So even though the spatial visualization levels were similar for business and lawyers, the business participants tended to have higher response time and higher accuracy than the lawyers and political scientists. So we would call this a time and error trade-off between business and law. And we didn't, however, detect any trade-off for math and computer scientists who had higher levels of spatial visualization, and then they were just as fast as the lawyers, but they were just as accurate as our business participants. So this indicated to us that cognitive abilities do interact with domain background to affect performance in both accuracy and response times. So we thought a lot of this could be explained by these different motivations. So what we found was that lawyers had far less motivation around approaching data visualization than business members and math and computer scientists. So we see in business and in math and computer science that they have to use data visualization a lot more in their career and studies. They put more effort into learning about data visualization. They're more confident around it. And then they're less anxious when math is involved in data visualization. So what we see here is that higher accuracy corresponds with higher motivations. However, it ties in with cognitive ability because when we enter spatial visualization, we then see the quicker response times. So we thought that these things could explain why business outperformed law and political science in accuracy across subconditions, because they place a high value on being accurate, while math and computer scientists might also place on high value. They have higher levels of spatial viz, causing their response times to be quicker. So this left us with 3 design implications. Our first one was that across all domains, overall performance is best if you just remain in Cartesian coordinate charts, and that accuracy is unaffected by density of those charts as well. We found that math and computer scientists were the least affected by chart rotation and task difficulty, but there were notable differences to account for the other couple domains. So for business professionals, they can be very accurate with rotated visuals, but then this will increase their response times. And then for lawyers and political scientists, any rotation at all of charts would lead to lower performance. So our advice was to choose one chart type and stick to it. And we really felt that this last implication was really important, given that a lot of international and influential bodies and governments and universities were creating COVID-19 dashboards of spatially rotated data. And we think designers should be empowered to cater to the abilities of those making high-impact governance decisions when sharing scientific information. So thank you so much. I hope that you are fully prepared to design your visuals when you go into your consultancy meeting. And I hope that I've been able to show that there is an interplay between cognitive and demographic factors that should be considered together as we're whole persons to increase effectiveness and inclusivity of visual design. Thank you so much.
All right, thanks, Sarah, for that talk. Once again, please use Slido to ask questions if you're there. But to get the question started, I'm really, really curious about generalization. So here, by that, I mean, what's your next group that you want to try this on? You've done business, you've done political science. I do a lot of work with scientists, but of course, that's a misnomer. What would you do next?
Love this question. I think it would be really interesting to study visual artists, actually, because they reportedly have high levels of spatial visualization. However, they have also really high levels of math anxiety and anxiety around doing visual tasks. Well, not anxiety around doing visual tasks, but anxiety when you add in the data component to it. So given that data visualization is really a marriage of data, math, and visuals, it would be interesting to compare them to how we do as a community of math and computer scientists.
I totally agree. That's a great group to try out next. I don't know. It's interesting how you compared the different subgroups, because I think if you fast forward in 10 years, data is going to be in even more places, and everyone's going to have to kind of learn and adapt to this. So it's an excellent thing to think about. We do have a question in Slido, so I'm going to read it off. Do you think the cognitive abilities in spatial visualization being measured come more from practice or from talent?
From practice or?
Talent.
Talent, okay. I would say definitely practice. Of course, there are some things that you might be good at when you start your day, but the more that you practice spatial visualization, the better you get at it. And there are a lot of studies that show that the more you spend your time doing spatial visualization tasks, the better you get, and then the more adept you'll be at interpreting data and interacting with data visualization. So if you're out there and you're wanting to get better at doing that, then there's a lot of ways to practice spatial visualization.
Yeah, please. Here, I'll hand you my mic.
Yeah, I was just curious, like, it almost seems like people in law and politics are feeling a lot of anxiety and kind of, especially in law, trained to move through material very quickly. But I'm wondering if you're seeing people like that just kind of being alienated by data in general and wanting to just kind of avoid it. And I feel like in a lot of situations, you're seeing policies put in place that almost reflect that, I guess, where people are like making decisions that are against the data. And so I guess I'm wondering, like, how do you see breaking through that? How do you see making data like more accessible to people who are not just not good with it, but like agitated by it?
Yeah, this feels like a personal question. Yeah, I think that as designers, as data visualization designers, it's important that we create visuals that are true to the information that we're representing and are accessible to everybody involved. So, I mean, a lot of that comes from people's past interaction with data and past interactions and bias towards different data. So I think as a community, if we do our best to be responsible to the data that we are given and try to tell a story and invite people into that story, then hopefully they will respond and we can make change that way. I think I might be running for office now, so I'll get off the stage.
All right, let's thank Sarah again. Oh, wait, I'll introduce you. So our next talk in the session is going to be local latent representation based on geometric convolution for particle data feature exploration. And the presenter will be Hao Yu.
Hi, everyone. I'm Hao Yu Lee from The Ohio State University. Welcome to my presentation. Feature extraction is an important task for scientific data visualization. Particle simulations are widely used in many domains, such as cosmology, molecular dynamics, and hydrodynamics. However, feature extraction is challenging in particle datasets for two reasons. First, in order to extract features inside the dataset, feature descriptors are always used. However, in particle datasets, defining feature descriptor is not as easy because there is no connectivity between the particles. Therefore, we don't know how to aggregate the local features. And features, they are usually defined both by the particle geometry and the physical attributes. So particle feature descriptors should combine information from both. Secondly, different scientific domains, they are interested in different kinds of features. Handcrafting a feature descriptor for each of them will become tedious sometimes. So to solve for this first challenge, we propose to use geometric convolution to define a feature descriptor. We use the particles within a radius to form a particle patch and detect the local feature inside the patch. After that, we apply the geometric convolution that decomposes physical attributes into different directions to combine the geometric feature and the physical attribute information. For the second challenge, an autoencoder is used to automatically learn the feature descriptor without much human intervention. Inside the autoencoder, the local patch feature is condensed into a latent vector. After generating latent representations for particle patches, we perform feature-related analysis in the latent space. Firstly, the features are extracted by hierarchical clustering of the latent vectors. To enable interactive clustering, we also design a feature exploration tool. Secondly, we apply mean shift tracking algorithm in the latent space to show that the latent representation can be used for feature tracking. Next, we explain how the feature is learned using a geometric convolution. So there are three major steps for that. First, the particle position and attributes are projected in different directions to learn the directional feature. And secondly, the directional features are combined to be a particle feature. And last, we combine all the particle features inside the patch to be the patch feature. So details of these steps will be discussed next. First, to learn the directional feature, we first define the learnable parameters on different orthogonal directions. The figure on the right shows a 2D example of this. And however, in 3D case, there are 6 different bases. And then we project the particle positions and the physical attributes of each particle into these 6 bases. And lastly, the position and the attribute vector is multiplied with a learnable parameter to get the directional feature here. The next step is to combine the directional features into particle features based on the angle theta between particle direction and the basis. We want to give higher weights to if the angle theta is more, so the weight function is the squared cosine of the angle theta. And particle feature is a weighted sum of all directional features all directional features from a single particle using this defined weight. Finally, we combine all the particle features in the patch into a single patch feature based on the distance between the particle and the patch center. Because nearer particles to a center will have higher influence on the particle patch. So therefore, we define a distance function that assigns higher weights to the particles with smaller distances. The patch feature is a weighted sum of all particle features, of course, using the distance function. We use the autoencoder architecture to condense the patch feature from like the last step I introduced geometric convolution into a latent vector. In the encoder part of the architecture, the introduced geoconv is used as a building block, while in the decoder part, we use geometric deconvolution, which is defined symmetrically to the geometric convolution. Details about geometric deconvolution can be found in our paper. To train this network efficiently, we sample about 1% of all particles to form the training data. The original data usually have uneven attribute distributions. As the left figure shows, the attribute distribution from one of our experiment datasets is uneven. So we found that direct training on this uneven distributed data may fail to capture some interesting features. So we use a sample method from a previous work by Biswas to sample the training data to have even distributions. The right figure shows a histogram after this sampling process. To demonstrate the usage of our generated latent representations, we perform feature extraction in the latent space by clustering. So since direct application of clustering algorithm in the latent space may involve a lot of hyperparameter training and back and forth visual examination of the clustering results. So we design a visual exploration tool to help this process. The figure on the right shows our visualization tool. The left panel is for hierarchical clustering. A tree structure is shown in the panel with a root representing all latent vectors. The users can click on the nodes to subdivide them into 2 or more clusters. The right figure shows a t-SNE projection of the latent vector into 2D, and users can identify visual clusters inside this panel and use that to guide the decision of subdivision. So in this example, we already find a node that's corresponding to a visual cluster in the t-SNE projection. After identify possible clusters of interest, the user can further analyze the clusters through a physical space particle visualization. So in our example, the visualization shows that the cluster of interest may contain features inside. but the background is not fully separated. So subdivide the node and we can find that one of the child node exactly contains the feature of interest. We also present another case study in our method evaluation. The dataset is from one of the supernova simulation. The top figure shows original data. We draw particles as semi-transparent spheres, so the high-density part stands out. We can see the connections between the future and the high particle density area. And the bottom figure, we show here these regions, like the interesting future regions, are extracted out as yellow particles using our method. We further investigate this case study. According to the domain scientists, the supernova core structure can be separated into the inner core and outer core. So the top left figure shows the particle's density, and the top right figure shows the particle colored by their temperature. We can see that inner core is corresponding to regions of high density and low temperature, while the outer core is related to high density and high temperature. So in the bottom, the figures show our method can separate the inner and outer cores, indicating our approach can capture features defined by multiple variables. Lastly, we show animations. The animations show the feature extraction tracking results. The left figure shows tracking in the latent space, and the right figure is tracking in the raw attribute space. The tracking position is indicated by the blue box. Our method have apparent better accuracy in this case. So in conclusion, we present a neural network-based approach to generate local latent representation for particle data, and that is used for feature extraction and tracking. So that's all for my presentation. Thank you all for attention and listening. I'm glad to take any questions.
Thanks, Hao Yu, for the talk. We actually have a question in Slido already ready to go for you. The question is this method rotation invariant?
I think this method may not be rotation invariant because of the geometric convolution we used, but rotation invariant may not be like always required for scientific data, which are like feature extraction, because the data, the feature itself may be defined by the rotation of the object itself. So yeah, that's my answer.
Awesome, thanks. I had a question while maybe people continue to type in Slido. You may have already said it in your talk, and maybe I missed it, so sorry. When you define your patches, you're using a radius parameter. Is it to set the radius parameter?
That's an interesting question. We actually have a method in our paper to do this hyperparameter training. It's based on, it's a method similar to like cross-validation. We use part of data to set the hyperparameter and use the optimization method to choose that. So yeah, I think that's a way we choose that.
Thanks. All right, I think to stay on track, we should switch to the next speaker. Hao Yu, thanks again for the presentation. You're next. Okay, it looks like we're set for our next talk. The presentation is going to be for the paper Graphical Enhancements for Effective Exemplar Identification and Contextual Data Visualizations. I do want to apologize. The program lists this talk as virtual, but we're actually lucky. We have an in-person presentation here to go for us, and the presenter will be Xin Yu. Take it away.
Okay, thanks for the introduction. So this is a joint research with Shenhui and Klaus. So exemplar identification is a problem of multi-criteria decision-making. It tries to find a set of desirable instances based on users' domain knowledge and preferences. Therefore, global optimal configuration doesn't exist, and the local optimum is up to the user. For each exemplar, there must be certain strengths on some attributes to dominate others, which is a form of Pareto optimality. Exemplars should also avoid the cases that have extremely excellent performance on some attributes, but quite awful on others, because such configurations are not feasible in many real-life applications. Here we have an example for exemplar illustration. Assume there is a wine shop that is going to import some brands of wine, and each kind of wine is evaluated by 12 attributes. The wine shop has limited shelf space, but still wishes to satisfy a broad customer base. The owner will find a set of wine that minimizes redundancies, and at the same time, he has to offer a well-diverse spectrum that satisfies most buyers by avoiding just extreme selections that only appeal to minority customers. Those brands of wine chosen by the owner are called exemplars. So from the example, it's common to see exemplar problems in many real-life applications, such as investment banking, where balancing a stock portfolio is a key to solid growth, and in drug design, where components have different side effects that affect different patient populations. However, such problem has not been well studied yet. Researchers on multi-criteria decision-making mostly tries to find a global optimal solution, while Pareto optimization fails to keep balance among attributes. So we solve the exemplar identification tasks by attribute contextualized data visualization, which is ACDV for short. In an ACDV visualization scheme, attributes and data points are visualized in a joint layout for users' exploration. So here is an example for ACDV. Here, blue points represent data, while upcoming red points represent attributes. It enables users to explore exemplars with 3 assessments. First, how similar a data point is to another, and how correlated an attribute is to another, and how strongly expressed an attribute is for a given data point. There are lots of ACDV schemes like Rabbit, star plot, and so on. We found that data context map best fits the need of users' exploration on data and attribute space. However, a basic data context map is suitable for preference set selection, but not enough for exemplar identification. Preference set finds instances that meet certain preferences, but they don't have to be Pareto optimal, neither do they care about the performance on non-preferred attributes. But exemplar set has stronger constraints. It tries to find instances that meet several preferences at once. So exemplars should reach Pareto optimal and attribute balance at the same time. To make the data context map satisfy exemplar identification tasks, we add graphical enhancements on it. We list 3 kinds of enhancements: the color encoding, density estimation, and contours. Contours are better than others we found since it reveals magnitude level, and the interval can be controlled manually to convey different accuracy level. We reviewed researches that compare 2D and 3D landscapes. We found that although 3D landscape looks more appealing, it doesn't provide extra benefits than the 2D scheme. So we just applied 2D and 2.5D enhancements in our study. The first graphical enhancement is ISO contour map. Once a user adds the value constraint on a variable, it will generate a single colored area to include all the data points that fit this constraint. The advantage is that users can easily learn which constraint each data satisfies, but it doesn't give additional estimation on variable values. So we apply multiple contours for a single variable to make up the shortage of magnitude level restriction on ISO contour maps. A progressive fading color scheme is used to reduce clutter when various color areas overlap together. With this enhancement, one can easily estimate the magnitude level of the data on a single variable. However, with the increase of attributes, color blending and mixed contours can be confusing, resulting to the problem of interpretability. So here is an example. It's hard for people to read this map at dense areas. Utility of this enhancement is limited to 45 attributes by experience. So the last enhancement is terrain map. Terrain map is come up to solve the problem of color blending and dense area distracting problems. It sums all the attributes together to unify different colors that arise in value shaded map. Users can learn overall magnitude of data set and its distribution from terrain map. 3D terrain is commonly used in geography, but 3D visualization is argued not to provide additional cognitive benefits because of the occlusion and perception distortion. So we implemented a 2.5D map with height emphasized by a color map and shading, as well as a fixed viewing angle to avoid those problems. We also constructed a user interface that enables users to identify exemplars by their own domain knowledge and preferences. The pipeline starts from the inputting data, and then the interface will generate the data context map layout. Next, users can pick up a graphical design on their need and set constraints by sliders. After that, the user can explore the map and find exemplars. In addition to that, we also devised a Pareto algorithm that explores directly from the original data space to find exemplars. It is used as a benchmark for user selections in the user study described later on. So here we have a short introduction to the algorithm. Given two terminal exemplars, our algorithm starts from one of them and searches a path to another. Points on the path are exemplars recommended by the algorithm. It constructs the graph by KNN and does Pareto optimization to filter out non-optimal configurations. Next, it does Pareto optimization on Euclidean distance, cosine distance, and magnitude to find the optimal successor. The search algorithm is guided by a heuristic function similar to A-star search. Then we did a user study to assess 3 different enhancements on the right. A bare data context map on the left, it was used as a baseline to compare with 3 graphical enhancements. And 4 data sets was used in the user study. And we invited 32 participants in the user study. And they were divided into 34 groups equally, and each group were tested with 1 design and 4 data sets. The order of data sets was totally shuffled. By given terminal exemplars and constraints in each data set, users were asked to find 7 to 10 exemplars in each data set. And we evaluated users' choices by comparing with the algorithm-generated exemplars. Here is the evaluation formula. For each user, we pick every exemplar from the Pareto algorithm and found the most similar one from the user selections. The similarity is measured by dot product, and the mean value is used to evaluate the quality of user-selected exemplars. So here, the final results show that all 3 graphical enhancements are better than the baseline, and the value-shaded map and terrain map are better than the ISO contour map, and value-shaded map and the terrain map, they are more competitive than each other. So although we can find some superiority from the strip plot, we had to prove the superiority statistically significant by some analysis. We first did a 2-way art ANOVA, where the art stands for the aligned rank transform. It is typically used when data is not aligned. Here the case is for data sets. And it shows that the difference among designs are statistically significant. And then we did a post hoc test to test the pairwise significance, and it shows that all the designs are better than the baseline, and terrain map outperforms the ISO contour, and the difference of value shaded map and the ISO contour map is just below the level, and the difference of value shaded map and terrain is not significant. So to conclude, we presented a novel visual interface for exemplar selection and presented a modified Pareto-guided search algorithm, and our study was verified by a between-subject user study. So thank you for your attention, and I'm happy to take any questions.
Thanks, Jinyu, for that talk. And once again, please use Slido for asking questions, but I'll get the questions started since we don't have any in there right now. I'm curious a little bit about scalability. And here by scalability, I mean, what happens if you need to have lots of exemplars or you have lots of classes you're trying to represent? What are your thoughts on that?
So users can select exemplars by their own need. For example, they set constraints and their target exemplars, and they can explore the map and select what they like. So this is not limited by the user's selection. But for our algorithm, our algorithm would recommend not too many, like 7 to 10 exemplars. So in the user study, we set this constraint for the comparison.
So in practice, just as a quick follow-up, do you think there's cases where you need more than 7 to 10, or is 7 to 10 kind of practical?
In some cases, like the Pokemon game, like in our data set, university application, like Pokemon, is enough for 7 to 10. But for other cases, they need more recommendations. It's also good, we can enhance our algorithm to recommend more, and we can also ask users to find more by our graphical enhancements.
Awesome, thank you.
Thank you.
Did you have a question? I think we have an audience question too.
Have you tested this in competitive Pokemon, and how successful has that been?
Sorry?
I mean, like, what was your test with Pokemon? And how, was that in like competitive play or what?
Oh, we find first we set constraints on those attributes like attack, HP, defense, but such Pokemon, they cannot be satisfied at once because there are no such Pokemon that is good at every attribute. So we set constraints for them and add to like targets. One Pokemon is good at attack, the other is good at defense, and then we ask users to find someone they are good, they are like make a balance among them, and our algorithm finds the Pareto optimal for them. It's more about a comparison of those attribute values, but we didn't test on the real game for that. Okay.
All right, thanks, Junyu, and we're going to get set up for the last talk of the session. And while our presenters set up, I think I want to point out the most unusual part of this session might be that never in my experience have I seen 3 presenters simultaneously presenting a paper, so we have a special treat for our last talk. All right, so our last paper is going to be Effectiveness Error, Measuring and Improving RADVIS, Visual Effectiveness. And our three presenters are Marco, Graziano, and Giuseppe. Take it away.
Thank you for the introduction. This paper is about RADVIS visual effectiveness. And let's start with RADVIS. RADVIS takes as an input a multidimensional data set, normalize it, and plot it on a bidimensional scatter plot, maintaining some relation with the dimensions. The point positions are at the equilibrium point between the spring forces that are proportional to the value of P. And the position of each point, in principle, a point should be closer to the anchors, having the highest P values, the dominant dimensions. And we define visual effectiveness as how much the order or the distances from P to the anchors reflect the order among its values. So far, so good, but how long will a simple visualization fool people? Present company excluded, of course. I see 2 really critical issues in RADVIS. The first one, while the spring metaphor is really intuitive, its consequences are not. Second, a non-curated dimensional arrangement produces a random and useless plot. In my opinion, using a random arrangement is not an option. To clarify my point, I'll use data from about these missionaries that are spreading beautiful visualization among people in 7 little islands. And, for each visualization, the data report the percentage of the people that like that visualization. And here we have a single point. It is about RADVIS. And looking at this point, what can you conclude on it? P is very close to A. Can we conclude that a large percentage of A people like RADVIS? No. A is only 15%. From a point position, we can get a dominant dimension, not values. It's a proportional story. A is bigger than other values, not big. Solution, training RADVIS users. Let's start again. This time is about PCA. What does the P position tell us? A is the closest anchor. Can we conclude that A is the biggest value? No. A is 0. Because B and G are the dominant dimension, but they pull P very close to A, causing a bad effectiveness. The solution, change the dimension order, rearrange them. It is intractable. Let's do that. How? Now, really nice. The plot correctly suggests that B and G are the dominant dimension, and A is the last one. Good effectiveness. If the arrangement is just random, we cannot make any claims on dominant dimensions. Here we have 200 different positions of the same point, 200, corresponding to 200 arrangements out of 20 million. Which one can we trust? And we have other issues around. Clumping, you know, you have man-to-man plotting, similar points, the similar points that are very close to each other. And so we have effectiveness, clumping, man-to-man plotting, and so on. And we got an intuition. Improving the effectiveness will mitigate also the other issues. 2 years of work. And again, how to get an arrangement we can trust. We got a simple algorithm that defines the optimal dimensional arrangement for a single point, the exact solution. It is surprisingly simple. I'll show you with an animation. We sort the point values in descending order. You arrange the anchors as follows. The first one on the top, the second one on the left, the third one on the right, the fourth one on the left, the fifth one on the right. You got the idea? And eventually, the point will be in the right position, exactly close to its dominant dimension. It is simple, tractable. The error is at 0, and we have a formal proof of that in the paper.
Okay, we know that this arrangement produces wrong insight. The question is how to measure the error. Starting from the optimal arrangement, we sum the number of swaps needed to reach it, weighting them with swapped values. The definition of the effectiveness error of a point can be easily generalized to a set of points simply by computing the average of the single errors. And for example, this dataset has an error of 0.5, and if we use a different dimension arrangement, the error improves. Now it is around 0.2, and a lot of points are green, meaning that they have a very low error. The effectiveness error can be used to distinguish between badly and correctly plotted points, and therefore to support the correctness of assumption that can be done looking to the Radwitz. So looking to this visualization, I can formulate some assumptions, like this group of points are close to the center, suggesting that each point has similar values among their dimensions. This group of points are close to budget and screen, so we expect that their values on budget and screen are the highest among their dimensions. This assumption makes sense, but without knowing the effectiveness error of the points, we cannot confirm the correctness, so they could be false. If we plot the effectiveness error of the point, we can understand that the first assumption is false. Points are red, meaning that error is quite high. The second assumption is true. Points are green, meaning that error is close to 0, and that their position is correct. Defining the best dimension arrangement that minimizes the error of a set of points is not an easy task. The optimal solution is intractable in most of the cases. In fact, this is factorial in the number of dimensions. And to cope with the problem, we define a heuristic that approximates the solution. It is inspired by the Trevelyan salesman problem and use a greedy strategy to allocate dimension in a polynomial time. So this is the same dataset of the previous example, where most of the points show an error, and it's not possible to make correct assumption. Look what happened if we apply the heuristic. Most of the points become green, so the error is very low, and now we can formulate correct assumptions. To evaluate the performance of our heuristic, we did a brute force analysis on 21 real datasets. First, we computed all the possible dimension arrangement of the datasets, plotting the distribution of the effectiveness error. And then we compared the optimal solution, that is the minimum value of error, with the effectiveness error produced by heuristic, that is the green point. The heuristic performed very close to the optimal solution for most of the dataset, and on average, it shows a very small difference of 0.55%.
But we continued this evaluation. So effectively, we get back to literature review, and we identified, first of all, a fourth issue. So well visualizing cluster in a separated way, and 5 main approaches that covered classic Radwitz in order to apply the same extensive brute force evaluation to them and evaluate the performance of our objective function. Looking at the first issue, clamping toward the center, we use a state-of-the-art metric, clamping error and mean distance toward the center, and we saw a clear edge of our solution with respect to all the others. Moving to many-to-one plotting, we used projection error in different form, and we saw that instead, dependent DA showed the best result, but our solution and independent DA showed similar and comparable result to that. Moving then toward effectiveness, we use a state-of-the-art estimation error and our novel introduced metric, and even in this case, we saw an edge of our solution with respect to the other. And finally, we use a DB index for cluster separation, and in this case, WitzRank and Radwitz++ show the best overall results, but all the approaches show comparable results. Interestingly, if we focus to all the 4 issues altogether, only our approach show or the best result or comparable result to state-of-the-art. That led us to asking, are those results confirmed when we have a user in front of a Radwitz conducting normal task? And so we conducted a task-based evaluation with a within-subject fashion based on 5 tasks and 32 participants. With results were evaluated with 2 one-way ANOVA tests on 2 hypotheses. The first one was that our solution was more effective than the best competing technique, and the second one was that it was better than the default arrangement given by the dataset. The tasks were eventually modeled as identify dominant dimensions for the user, explore point similarity, comprehend data overview, analyze clustering results, and detecting outliers. And here we have the results with the support of the ANOVA test. Eventually, we saw that 5 of the hypotheses were supported at p-value lower than 0.05, and 5 were rejected. But interestingly, if we focus for a moment on the task T1 and T3, we see from the box plot an edge of our solution with the other and a complete support for statistically significant results, meaning that the first 2 results for clamping toward the center and effectiveness were confirmed by the user study. For all the other remaining hypotheses, we took the strict rule to consider the user study not significant, even if just one of the hypotheses was rejected. And for this reason, the rest of the task show a comparable behavior between the tested techniques. So concluding this talk, in this paper, we provided means to improve Radwitz visual effectiveness in the form of a novel metric to assess the quality of the point position, an algorithm that computes the exact 0-level position of the point, formally proofed, an objective function that shows overall better result, benchmarked both numerically and with a user study, and finally, an heuristic that makes this approach actionable in linear time. Eventually, we consider even the introduced metric as belonging to the broader class of metrics used to evaluate the quality of dimensionality reduction projection, where Radwitz is one of them with the characteristics of preserving original dimension. And additionally, we are trying to extend this approach to other spring-based plots like star coordinates. With this, I conclude my talk with a slide that lists you all the available resources from the D3 plugin with which you can implement easily D3 Radwitz to the experimental environment that we use in which, as shown in the video, you can see the results coming from the benchmark. Thank you for the attention.
Thanks to all 3 of you for the excellent talk. I think we only have time for one. I'm not seeing anything in Slido, so I'm going to ask my question, which I want to connect some dots between things that we've seen already in this session because it's had such a diverse set of papers. And one of the things I'm curious about is, have you thought about effectiveness error with respect to potentially overplotting? We had a talk earlier about overplotting and how you do exemplars to avoid it. What do you think about that?
Sorry, can you repeat the question? Because there is a little bit of echo.
Yeah, sorry. It went in and out. That's my bad. What happens if your effectiveness error metric positions the points and creates additional overplotting, where they're all now mapped on top of each other?
The sides of the point, you mean?
Yeah.
You're right. We pay a trade-off. To display the color on the point, we need a little bit bigger point, but the value is enormous. Without the color, you don't know if you can trust the point position. This is the point. Nothing, you can know nothing about that.
All right, with that, I think we have to conclude our session to stay on time. Thank you everyone in the audience for participating, and thank all of the speakers one more time for our excellent diverse set of talks.